Okay, so first I'd like to mention that this is joint work between collaborators at University of British Columbia, ETH Zurich, and NYU. REST type system is special. One of the things that makes it special is that it tracks the notion of ownership. So values in a REST program are owned by places, assignments transfer this ownership from one place to another, and by default, these values can only be directly accessed by the places that own them. But as we've seen before, programming exclusively in this style can be quite restrictive, so the REST allows for borrowing. And this borrowing transfers this ownership from one place to another temporarily. And this is tracked by the type system. So while a place is borrowed, the type system places restrictions on how it can be used. So these features of the REST type system make it more restrictive. But we are willing to abide by these restrictions in order to obtain guarantees about our program. Perhaps the most famous guarantee is that if we operate within these constraints, the REST compiler will ensure that our programs are memory safe. But there is another important but less obvious benefit of this, which is that these type system restrictions facilitate reasoning. And in particular, they enable modular reasoning. So what I mean by modular reasoning is the ability to verify properties about a REST program just by looking at individual functions in isolation. So for example, we can tell that this assertion will always hold in a REST program regardless of concurrency or how f is called. The reason we know this is that the REST type system ensures, amongst other things, that callers of f will pass in distinct references for x and y, so the second assignment cannot change the target of x, and the assertion will always hold. So REST developers often reason informally in this way, and we would like our analysis tools to be able to do this kind of reasoning too. In order to do that, an analysis tool will require a model of REST ownership and borrowing in order to take advantage of these guarantees. And a model is like a data structure that explains the borrowing of the program, and the development of such a model is the focus of this work. So now imagine that you are building a REST analysis. You'll probably need some model, and your choices at this point are either to make your own model for the purpose of your analysis, or perhaps take an existing off-the-shelf model. So if you try the first approach, you'll probably realize that this is not easy. For example, your analysis might be concerned with when a particular borrow in the program expires. And this is challenging because there's no information on the surface that provides this. There's no, say, like syntactic annotation indicating when x expires. And to answer such questions in general would require your model to be about as precise as the REST compiler itself. So that's probably not a good idea. Instead, maybe you try a general purpose model. And the good news is that there are many existing models of REST. And the bad news is that they all aim to capture different aspects of the type system. So then you would need to decide which, if any, of these analysis tools would be suitable. So let's take a look at what analysis tools want to see in a REST model. And by analysis, I'm speaking somewhat broadly to also include program verifiers. So many of these tools want to take advantage of the modular reasoning guarantees provided by the type system. And in order to do that, they need a model that can summarize borrowing across functions and loops. And preferably, we would like this to be automatic. Second, we would like a model to have a close connection to the REST compiler's internal representation. So this might seem like it's an implementation detail, but it's actually important for a more fundamental reason. And that is that the REST language does not have a formal semantics. So the closest thing we have to the formal semantics of REST is whatever the compiler decides to do. But another reason is that REST compiler has designed very nice intermediate representations. Analysis tools like to use these, and being able to use the same representation for the model and the analysis without having to do translation reduces places where soundness could get introduced, or unsoundness could be introduced, rather. Sorry. Finally, we would like the model to be able to reason about sets of borrows. So in REST, you can have like individual borrows, but users can also define data types that contain sets of borrows inside of them. And the type system tracks these in kind of interesting ways. So for example, all of these different fields contain sets of borrows under the same lifetime, but the type system ensures that these will all be distinct sets of borrows. And your analysis tool might want to take advantage of this, so the model should reflect that. And so prior to our work, there was no model that could satisfy these three properties. So now I'll introduce our model, which we call place capability graphs, and I'll call PCGs for short. So it creates these modular summaries by taking the results from the borrow checker after the type checking of the program. It connects to Rust internal representation by capturing notions of ownership and borrowing analogously to the Rust compiler itself. And it's able to reason about sets of borrows via a novel construct that we call lifetime projections. Now I'll give an overview of the model. So our PCG analysis takes a function as input and computes this data structure for each program point. And we call our data structure place capability graphs because it associates places, which are roughly memory locations, with capabilities. And these capabilities describe what the compiler thinks can be done on these places at a particular point. Now, we chose the capabilities ourselves, but they correspond naturally to restrictions that arise on places from the type system. Nodes in the PCG describe memory locations, so these can be either places or these lifetime projection nodes that store a set of borrows stored under a place. Finally, edges in the PCG denote temporary transfer of capabilities. So for example, when a borrow is created in the program, an edge is introduced that describes the temporary transfer of ownership from the borrowed place to the borrower. We use unpack edges to split structs into smaller pieces so that you can move out individual components. Abstraction edges are used to summarize borrowing across function calls and loops. And there's other edges that are described in the paper. I want to highlight a couple other features of our analysis. So we track path-sensitive information about borrows created under different control flow paths. So this could be useful for, say, program verifiers that want to care about path-sensitive aliasing. In addition to producing these graphs, our analysis also generates annotations. And so these annotations roughly correspond to the actions taken to update the graphs through the course of the program. And tools can consume these annotations, for example, to generate memory safety proofs. Finally, our model supports many advanced use cases of borrowing, including operations on nested references. So when I say nested references, I mean references that store objects that they themselves store other references. And it turns out that reasoning modularly about operations on these nested references can be quite challenging. So in the paper, we described the features of our model that allow us to support that. Moving on to evaluation, we wanted to look at 3 different aspects of our model. So first, we wanted to see how much real-world Rust code we could support. Second, we wanted to see the extent to which we captured these ideas that we intended to, which is restrictions imposed by the Rust type system. And finally, we wanted to see the extent to which we could integrate our model into real tools. So to answer the first question, we went to crates.io and got the top 500 most popular crates and performed our analysis on every function on the crates to generate models. And our results were quite nice. We were able to generate models for almost all of the functions. About 2% we couldn't generate models for because they use features like raw pointers in line assembly that our model doesn't currently aim to support. And for a very small amount, we think we can resolve those with some more engineering work. Now, for the second question, we wanted to see that our PCGs were faithfully reflecting the constraints that the type system imposes. And so namely, if in the graph a place is lacking some capability, that means the compiler should prevent this place from being used in some way. So to evaluate this, we took a mutation testing approach where we would use our analysis to systematically generate programs that don't type check. So we would take a function from our corpus of functions from the 500 crates, generate a PCG at some point in it, identify a place lacking a capability. So here, the PCG is indicating that at line 3, vec does not have a capability because it's being borrowed. Then we would systematically generate a program that violates this constraint here by moving out of vec while it's borrowed. And then we would send this program to the compiler and confirm, verify that the compiler rejects it. And this worked nicely for us. We generated 7 million mutants, and almost all of them got rejected. And if you're curious about the 0.01%, feel free to ask after the talk. Finally, we wanted to look at the extent to which we could integrate our model into real analysis tools. So we looked at 2 tools. First is Prusti, another project that we're working on. This is a deductive program verifier for Rust, and as part of its verification, it synthesizes a memory safety proof in Viper. Now, previously, this was done via an ad hoc analysis that could capture simple borrowing patterns, but didn't support a lot of real-world patterns like borrowing across loops and structures holding references. So we got rid of that and instead put the PCG in and had the Prusti implementation synthesize memory safety proofs just by reading off these annotations. And this allowed us to simplify the code base of Prusti and at the same time enable it to support more Rust code. The second tool we looked at was Flowistry. So this is a much different type of tool. It's an information flow analysis tool. And Will Crichton, the creator, had actually recommended this to us because he mentioned that internally it's using this ad hoc alias analysis to compute some results. So we took that out and had created a fork of Flowistry that instead queried the PCG. And as a proof of concept, this was successful. The behavior was equivalent to the original, and it passed the test suite. Now, what I want to highlight is that in both of these cases, the integration with the PCG was quite easy. All that the tools had to do was basically query the PCG API to get this information out, because both of the tools were written in Rust, operated on Müller, so it was a very sort of direct extension. So in conclusion, we've shown that these models are necessary for Rust analysis tools, identified that none of the existing models really satisfy all the criteria we would like in general. We developed place capability graphs, which is a model of Rust ownership and borrowing that can satisfy these criteria. And in our evaluation, we showed that our model can support a lot of real-world Rust code and is easy to integrate into existing tools. So if you're building a Rust analysis tool and your tool requires some notion of ownership and borrowing, please try our model. It's available on GitHub. You can include it as a crate in your project. It works. And you can also reach out to us on Zulip. That concludes the talk. Thank you very much.
We have some time for questions.
Thanks for the great talk. How much of the model how much of the assumptions, or let's say the invariants of the Rust type system are needed for your model to work? I mean, specifically, if I were to try a different language that allows mutable aliasing, could I use the model to use different capabilities and things would still go through and I could represent things? Or are there sort of assumptions that things behave the Rust way?
Yeah, that's a great question. For the most part, we keep assumptions minimal and trust the compiler to give us correct information about aliasing. So for example, our analysis doesn't require a particular borrow checker implementation. So we query certain borrow checking facts from the compiler, but we don't sort of verify any properties or make any assumptions about them. So I think extending the model to support other languages would be, or extend even other extensions of the Rust type system would be possible, yeah.
Cool, and when you say you extract these from the borrow checker facts, is this like the Polonius implementation and this data log stuff that you end up with the same facts and you turn them into your model?
So we support both the Polonius borrow checker and the current borrow checker, because Polonius actually is very slow, so we also support the current borrow checker as well. And you end up getting different graphs for the different borrow checkers in cases where the behavior is actually different.
Cool, thank you very much.
Thank you for a very clear and well-composed talk. When you were saying that you are extracting information from borrow checker and you were checking whether your borrow checking is complying with the Rust borrow checker, you said you're mutating the programs and then you're running your borrow checker, but how is it possible if the Rust borrow checker will fail on these ones?
Okay, so to be clear, what we're doing is we get the borrow checked program, and then we make a new program that we want to not borrow check. And so we're validating that it actually doesn't borrow check.
Yeah, but how your tool runs if you rely on Rust borrow checker?
So our tool only operates on programs that will borrow check. So we don't attempt to generate graphs for these mutant programs. For those, all that's done is sending them to the compiler just to make sure that the compiler refuses to compile them.
But how is this testing of your tool and not just testing of Rust-C?
So what we're testing is the way we're encoding these capabilities are actually reflecting the compiler. So just for example, if we were able to make a mutant program and the compiler accepted it, that means there's a restriction in our graph that doesn't actually agree with the compiler. We could talk more after if.
Yeah. Thank you.
Can you give me a sense of how much information you extract from the Rust compiler versus how much information you synthesize? I didn't quite understand whether you were using, say, lifetime information at some point to inform your algorithm or not.
So for loops and function calls, we get all of that from the Rust compiler.
Okay.
For assignments, we basically do that ourselves because assignments are quite easy. And then for like control flow information, this is just from the control flow graph.
Okay, and perhaps I missed this also. Do you have an argument that you will always, you have a more formal argument as to why you are consistent with the Rust borrow checker? Or do you think there might be programs lurking that the borrow checker will accept and that you may fail to justify in PCG?
So based on our like top crates analysis,
okay.
That would give that. Another thing just to mention is that indeed the REST type system, we don't have a formal soundness, but for tools like Prusti that synthesize memory safety proofs, if the memory safety proof goes through, that's a pretty good argument, I suppose.
Yeah, sounds good. Thank you.
Thanks.
Let's thank Zach again.